Okay, so good evening, everyone, and welcome to uh, today's asset colloquium. And before I go ahead and introduce welcome to the speakers, I would like also, on behalf of the Asset Forum, wish you and all your family members a very happy New Year. I hope this year will be much better than the year that has gone by. So today we have two speakers in the set colloquium. They're going to kind of share roughly about 35 minutes and 20 minutes respectively. They're going to speak on the part of the upgraded GMRT asset colloquium series. Today's title is Radio Frequency Interference Survey, Monitoring and Mitigating at GMRT. So that is the title of the today's colloquium. This is going to be, as I said, given by Mr. Pravin Raybole and Mr. Santaji Katore, both from, of course, NCRA-TIFR Pune. I will take a couple of minutes to introduce both the speakers and then request them to make their presentation one after the other. I request that the questions and discussion we can have after the end of both the presentations. So with those words, let me go ahead and formally introduce today's speakers. Pravin, who is an engineer dean now, joined the NCRA-TIFR in August '95. He acquired in Bachelor's of Engineering, Electronics and Telecommunication from Katore, Wadia Institute of Technology, Pune University, and Diploma in Electronics and Radio Engineering, that is DERE, also from the same institute. He has over 25 years of work experience at the GMRT Observatory, so that way he's a veteran. His professional experience is in the radio frequency interference, of course, about which we are going to hear from them today. The RFI mitigation, RF4 fiber and optical computer network. We also heard briefly about, actually in detail about this in the previous talks on GMRT the last few weeks. He has presented papers at RFI 2010 RFI mitigation workshop, Groningen, Netherlands, URSI 2017 at URSI General Assembly and Scientific Symposium, Montreal, Canada, and also at the IEEE International Microwave and RF Conference last year at IIT Bombay. Santaji, he is an MSc in physics. He's a scientific officer D at GMRT. He had joined GMRT in August 2000 as a telescope operator and operated the telescope over 13 years. And after 2013, he started working as a software developer for various subsystems of GMRT. Currently, he is involved in the projects like automated telescope scheduling, satellite RFI mitigation, servo-mechanical system data analysis, primary beam measurements, web-based monitoring and observing tools, and control and monitor systems, etc. So we can look forward to very, very interesting colloquium today, which is going to be given first from Pravin, and Santaji is going to take over from him. So over to Pravin.
Thank you. Thank you very much, sir, for your introduction. I wish everyone very happy New Year to all of you. And along with Santaji Katore, will be presenting the talk on this radio frequency interference survey, monitoring and mitigation method applied at upgraded GMRT. So my screen is visible to sir, everyone?
Yes, yes.
Okay, fine. So in the content of my talk, I'll be giving an introduction to GMRT, then the new RFI sources after GMRT upgrade, then effects of RFI on radio astronomy signal, how we do RFI monitoring and survey to find out these RFI sources, then RFI mitigation methods applied by using shielding technique or rejection, zone of avoidance and coexisting method. And I'll be giving an example of this building inside a Faraday's cage, and at the end we'll be talking about real-time satellite tracking and monitoring system. So before going to the RFI mitigation techniques, I would like to say that sensitivity of a radio telescope. We know that all the in most of the world, the radio telescope are very sensitive, and they receive very weakest signal from farthest galactic sources, and they measure the signal strength in units of Jansky, and 1 Jansky is equal to 1 into 10 raised to minus 26 watt per meter per hertz. And if I give one example,
Pravin, can you hear me?
hello,
Pravin, can you hear me?
yes,
Your audio is not that comfortable, and maybe you have to come closer, or is it possible to use earphones?
now am I audible now?
Now it is better. Yeah. So therefore, probably you have to come closer to the computer.
Okay, fine.
Yeah. Okay.
Is it fine, sir, now?
Sorry?
Is it fine now?
It is better. And of course, once in a while, your Wi-Fi is going a bit down. But in that case, you might have to switch off your video. But I'll let you know. But right now, please keep it on.
Yeah. So, hello. Hi. Yes. Now, I would like to I would like to give one example of our regular GSM handset, which has a sensitivity of minus 111 dBm, and the 1 Jansky is equal signal is 93 dB below the GSM handset sensitivity limit. Now, to check the sensitivity of radio so I would like to give one example of GSM handset mobile. If any mobile which we use for our day-to-day communication, which uses 1 watt of power, which is around plus 30 dBm, and when we move away from any base station transmitter, our link connectivity goes off, and our mobile says there is no link connectivity. And if we use this 1 watt transmitter at a distance of 100 times the distance of moon, the radio telescope, our GMRT radio telescope, will receive that signal, and will say that uh, there is a transmission of 1 watt transmitter at 100 times distance of moon. So the best known sensitivity of a GMRT telescope is around 0.03 millijansky. Mainly what we see, the most of the radio telescopes are far away from heavily populated areas. And in this example, we can see that in the table given below, we can see the GMRT is situated around east of GMRT is situated 80 kilometers north of Pune, and the population density you can see, which is around 7,214 kilometers. Sorry, 7,214 peoples per square kilometer. And whereas if we see the example of Meerkat radio telescope, the population density is only 2.8 people per square kilometer. So the GMRT, in this image we can see the array of GMRT antennas, which are spread in 30 kilometer diameter. They are of 45 meter diameter, and you can see they are marked in red pinpoints, and in the blue color, which is a 30 kilometer diameter circle. So radio frequency interference sources are, we can categorize these radio sources in two categories. One is external source, and other is an internal source. External sources are intentional sources, and internal sources are unintentional. So this is an example of external sources which are intentional. We have this example we can see the example on the screen that there is a FM transmitter, TV transmitter, satellites, etc, radar, from which we get all strongest signal, and they are transmitting at their allocated frequencies. So you can see the FM transmitter which has very high power of order of 100 watt to 20 kilowatt. Then television transmitter, you can see they transmit from 10 watt to 20 kilowatt. And if we see radar, they can transmit around 10 kilowatt peak power and around 200 watt of uh, average power. So these are very quite strong sources. And there are unintentional sources also which do radiate in broad spectrum, and we can see the example like switch mode power supply, UPS, then welding machines, our laptops, PCs, all the networking cabling devices, they do radiate at their multiple of clock frequencies. And also in the unintentional radio interference, you can say one can see radiation coming from wind towers as well as high power lines. So in this spectrum, what I would like to show that this is a spectrum for uh, 0 to 3000 megahertz. X-axis is a frequency axis, which is from 0 megahertz to 3 gigahertz. Y-axis is the amplitude, and this is the RFI ambience uh, present at GMRT observatory, which was taken on in the year of 2008. And these blue lines, what you can see, which are marked as a FM transmitter, TV transmitter, then GSM transmission, and you can see some lines at satellite transmission, then shortwave communication. So this is a typical RFI ambience seen at GMRT. Now, the GMRT receiver, there are 4 bands in which GMRT observes. So this is one spectrum of receiver system at band 2, which covers frequency from 120 megahertz to 250 megahertz, and in which what you can see, the pink line is a allocated radio astronomy band, and the other bands are allocated for fixed mobile communication, terrestrial TV transmission, aeronautical transmission. And you can see there are a couple of television transmission you can see, which is coming from Pune Doordarshan, Mumbai Doordarshan, Aurangabad Doordarshan. And on the left side, you can see the air traffic control, which is transmitting at 108 megahertz to 137 megahertz. So the another example we can see here, the spectrum is for 250 megahertz to 500 megahertz band, and in which you can see in the blue purple color, these are the US military satellite which transmit frequency from 240 megahertz to 270 megahertz, and these lines uh, are seen throughout the world. Any part of the world if you go, you can see these frequencies. On the right hand side, you can see now Doordarshan, earlier there was an analog transmission. Now Doordarshan has started their digital terrestrial transmission. So you can see the Mumbai DTT transmission is at 470 megahertz to 478 megahertz, and there is another transmission by Aurangabad DTT at 486 to 494 megahertz. And these are, if you see, this spectrum is a broadband spectrum, and the lines which you are seeing are a single line spectrum. And here in the middle, you can see the MEO satellite mobile user objective system, which transmit from 370 megahertz to 380 megahertz. So these are the kind of radio lines which we are seeing in the output spectrum. For the uh, for the band 4, you can see the spectrum for 550 megahertz to 900 megahertz, and in which you can see the mobile transmission at 824 megahertz to 890 megahertz, which is transmitted by Reliance Jio, and this is another GSM transmission at 890 to 960 megahertz, and this rest of the band is quite clean. So any radio observatory needs a very clean band for observation. So I will come to this now, effect of radio frequency interference. So what happens to our receiver system? So due to presence of these strong signals, our sensitive radio receiver system gets into saturation, and in many times intermodulation distortion products are appear in band due to outside band interference. So I will give you few example of how this interference affect the radio GMRT radio receiver system. So this is one example of band 5 in which you can see this is a in-band signal on the left side, where the first two lines are coming from mobile GSM and CDMA, and due to saturation, what you are seeing, the product of this F1 is 885 megahertz, F2 is 959.7 megahertz, and the IMD product which is coming at twice F2 minus F1 is 1034.4 megahertz, which is indicated by red marking. And when you move your radio telescope or antenna away from this mobile tower, you can see that line has disappeared. So this is one kind of in-band RFI which is coming due to outside band signal. So there is another example on the screen in which you can see the TV signal which is transmitted by Pune Doordarshan, which is the operating frequency is 535.35 megahertz, and this is a Reliance Jio signal at 882 megahertz, and F1 minus F2 882.17 to minus 535.17 megahertz, that lines come around 346 megahertz. You can see due to this outside band signal, you can see these products are generated in the main radio observatory signal. So how do we monitor and survey these sources? So I'm giving you one example that in the year 2016, there was a ExoMars mission in which this Schifferelli separation event was there, and GMRT telescope antenna were used to directly observe the UHF frequency, and that Schifferelli separation during that when it was entering the Mars atmosphere, which was radiating at 401 megahertz, and we were observing that particular frequency by using our radio telescope. And during that event, what we have seen that the line which was transmitted for that space-to-space communication, we have seen there were another two lines nearby present during that observation. Those two lines were at 402 megahertz, 402.8 and 402.7 megahertz, and we were surprised why these lines were present there, and we started investigating how to check them from which location it is coming. So we started acquiring that data for a couple of days, and you can see here this is a grayscale plot in which the x-axis is the frequency, y-axis is time, and we have recorded data from 380 megahertz to 403 megahertz, and these lines which are bright spot what you are seeing, it was a transmission coming from unknown transmission was coming from western direction, and that transmission was quite was coming at this time means zero from early morning 5 hours to 7 hours, 9 hours to 10 hours, and 30 hours to 19 hours. So we started trying to find out the direction of the RFI and source of RFI. So during our survey, what we noticed that whenever we are taking measurement near the hillside area, there were multipath reflections, and on on all direction we are seeing the RFI was indicating in all directions. So while uh, taking all the measurement, we came up to Bhimashankar, and there that was the highest peak point where we could see the other part of area, and from this location we were able to find out that particular line was coming from western direction, which was indicating towards Mumbai region. And and so when we approach, this line was coming from Mumbai region, and we came to know that that line was used by Indian Meteorological Department, and what that line was is a balloon, hydrogen or helium filled balloon, which is sent by all IMD department from airport at GMT 0 to GMT 12. So all over world, these balloons are sent at GMT 0 and GMT 12 respective time all over world, and they use that frequency from 400 megahertz to 406 megahertz, and you can you these frequencies are user selectable. So this is a payload where you can see the transmitter, which is used to measure the pressure, temperature, and relative humidity. There is another example where you can see in the nearby villages, people are using cable TV network, and this cable TV network is leaky. People don't use proper termination, and you can see the kind of spectrum which is seen on the screen. The red line is a leakage coming from cable TV. The blue line is a spectrum which is we expect, and this is a one kind of radiation coming from cable TV network. And why it is coming? So you can see the cables which are used, they are made with the improper cable joint, and the node or cable TV node or amplifier they use without proper termination. So if we use proper cable termination, you can decrease the emission coming from these cable TV cables. So there is another example in which you can see this is an array antenna in which we were reported one strong radiation coming from this E3 antenna. And while surveying, what we came to know that people are using this mosquito repeller at their house, and it also radiates broadband spectrum. So this is another example of broadband spectrum, and we have to identify this, and by surveying and using direction finding antenna, we could locate these mosquito repeller. So in the year 2005, we have also used in the GMRT surrounding area, people were using TV boosters, and those TV boosters were causing a lot of RFI due to saturation and oscillation of the TV booster. So we have visited around 1800 houses and rectified the TV boosters in the over a period of 3 years, and only a simple solution were provided, that one single resistor was given to added into the amplifier, so that that amplifier was not going into saturation. So another example is that the how we coexist with the external agencies. So GMRT is surrounded by many villages and smaller towns, and you can see this is a graph for the mobile towers surrounded around GMRT antennas. So there are around 245 mobile towers around GMRT antenna, and we are trying and negotiating with these mobile tower operator, trying to shift their frequency of operation from 8 CDMA 800 megahertz and GSM 900 megahertz to 1800 megahertz, so that the GMRT frequency of observation is from 50 megahertz to 1500 megahertz, and if they move away, so it will be less affected by these strong mobile transmissions. Also, we are doing constant monitoring of industries around GMRT. So we have one setup. We have set up with District Industry Center of Maharashtra, and we give no objection certificate to all the industries which are operated in and around GMRT telescope array. So you can see in this spectrum there are indicated by different colors. So the red mark are the red color for fabrication of bricks and building construction related factories. Then green ones are agriculture related factories. Yellow color is indicated with tire, polymer, PVC. So different industries, we keep on monitoring their operation, measure the RFI ambience there, and suggest also solution to them. So there is another unintentional source of RFI, which is a wind turbine generator. And what we have done is we have visited many wind turbine generator site and estimated the amount of RFI generated from this wind turbine generator site. So in this example, what you can see on the left side, when generation is on, you can see this red spectrum where the power line interference is coming from that particular substation and that particular area. When generation is off from the wind turbine generator, you can see there is less RFI, and these measurements were done at 1 kilometer, 2 kilometer, 1 to 8 kilometer, and you can see the clear effect of RFI from wind turbine generators. So at the site, what we have also noticed that these are the various locations through which the leakage was coming from the wind turbine generator site. So we have given various suggestions to these operators and given various shielding techniques so that they can coexist and we can coexist in the area. There is another example of power line interference. So since we are operating in 30-kilometer region, there are various high power tension lines which are crisscrossing the area, and what we are measuring all the RFI which is coming from these high tension lines. So what we are doing, we are using ultrasonic detector to measure the power line RFI. By pointing this ultrasonic detector to the radiating site, you can pinpoint the radiating source. This is one way of measuring the RFI. So we have adding, we do regular survey of these sites and take data of these fuse links, pin insulator and transformer, and by taking this data, we share this data to local MSCB office, and they attend this problem and rectify this problem. So this is a one example of RFI which is coming from 400 kV power line, and this is a spectrum with zero span with zero span, and you can see every 20 millisecond you are getting the power line interference on the spectrum analyzer. And this is using a log periodic antenna and spectrum analyzer setup. So by using the radio telescope also, we can identify the source of RFI. This is one of the technique which was used by Ulipen, Dr. Ulipen, for epoch of reionization work at GMRT. And with the his measurement method, we could be able to find out the source of RFI. So one can see this is a 440 kV AC line, extra high tension line, which is 18 kilometers away from GMRT antenna. And this is a hanging wire which was there and which was causing a lot of RFI coming from that particular location. So this is another example where you can see another hanging line wire on the 440 kV line, which was located using the pin ultrasonic detector. So what are the mitigation technique being used at GMRT? So there are first solution is hardware solution, where you use notch filter for all the external intentional sources. Then shielding measures like a shielding enclosure for self-generated RFI. Then another solution is a software solution, which is a real-time software solution for one is a real-time satellite tracking, aircraft monitoring, and real-time filtering. The another method, the third one is a coexistence. So coexistence with wind turbine generator, mobile phone network, power line distribution network, and negotiate with cable TV operator, wireless services, DTT transmissions. So in this example, what we are seeing, this is a front-end receiver system in which what we have used a 60 dB notch filter, which is tuned at 885 megahertz, and which is cascaded with CDMA GSM bandpass filter. So this is a antenna, this is a low noise amplifier, and this is a notch filter which is in series with the cascaded system. So in the hardware, how these notch filters are tuned. So you can see the FM, which is the frequency of operation is 88 megahertz to 108 megahertz notch filter, and which gives around 40 dB rejection. So likewise for police wireless transmission, then for TV transmission, and for satellite, we have used various notch filter, and which gives better than 40 dB rejection. So this is another example of a TV notch, which is the terrestrial transmission is at 530 megahertz to 545 megahertz. And this another example is for GSM CDMA notch filter, which is tuned for this 820 megahertz to 960 megahertz. So in this band, all the signals are attenuated. Apart from this notch filter, we have designed and developed various shielded enclosures, and so that the unintentional radiation coming from these devices are minimized. So this is an example of Ethernet enclosure, where you can see Ethernet switch is placed inside the shielded cage, which is used with AC power line filter and shielded Cat5 cables, as well as shielded and filter LAN connectors. So if we see the radiation coming from these switches, so these are the different Dell make, Cisco make, D-Link make switches, where you can see different spectrum, RFI spectrum. This is a kind of broadband RFI spectrum coming from these devices. So by using shielded enclosure, you can minimize this radiation. So in this, what is the isolation performance of that shielded enclosure? So what we have done, we have used a spherical dipole antenna, which is placed inside the shielded enclosure, and check the radiation level at 3-meter distance by using log predict antenna. So this is a isolation performance, you can say, from x-axis is 0 megahertz to 2 gigahertz, and up to 1 gigahertz you can see 80 megahertz to 80 dB to 25 dB. You can see the amount of isolation we are getting. So likewise, in the observatory, we have given various solutions to most of the devices which are causing interference. So this is one example of computer. Then air conditioner. Air conditioner also the control and control system which radiates stronger radiation. So we have given a shielded solution for this. The UPS also do radiate, so we have given solution to UPS and various digital control and monitoring system where they have been put inside the shielded enclosure. So the another example, you can say, every day we are using LED panels, LED tube lights, and which also do radiate very strong and broadband radiation. This is an example. You can see the red line which is on the x-axis, where this is the radiation coming from these LED tube and panels. So by providing shielding solution, you can see the entire radiation has been minimized. So along with this, we have used fiber optic network at the GMRT, so that the radiation coming from Cat5 cables and other electronic devices is minimized. So this is another example of cable TV amplifier where we have put inside the shielded enclosure, and you can see the isolation performance from 70 dB to 20 dB, which minimize the radiation which is affecting the radio telescope. So apart from this, in the GMRT observatory, we have used built a multi-purpose building facility which is inside the shielded Faraday's cage. So while building this shielded Faraday's cage, we have taken enough care, and you can see at the plinth level we have laid a shielded stainless steel mesh, and this mesh is integrated with these steel bar at the plinth level, and all these steel mesh is connected with the earth plate. So the entire building at the plinth level, which is almost on all six sides, which is covered with the shielded mesh. In the lab, which are inside the multi-purpose building, so you can see how the efforts we have taken here. The stainless steel mesh is of which is spot welded at every location by this spot welding machine. And in the lab, we have used a copper mesh for additional shielding, and this copper mesh is also soldered on all 6 sides. While taking all the HVAC system like heating, ventilation, and air conditioning pipe inside the building, we have taken enough care so that any radiation will not come out of the building, as well as there is no radiation getting inside the building. So this is an example of waveguide where the air conditioner which are with the HVAC pipe which are taken through these waveguides, and these are the power line connection are taken through filter connections. The entire building is structure is bonded to the earth electrode system. So this earth electrode is connected at each corner and every 6 meter distance. So after this, we have measured the shielding performance of this multi-purpose building, you can see the isolation performance of the multi-purpose building, where we have used a radiating source inside the building and measure the radiation level away from the building, 10 meter away from the building, and you can see the isolation which is quite good, and from, you can say, average isolation is around 50 dB. So apart from this, I'll take another 2-3 minutes only. So uh, apart from this, we are this is our current plan to track the flights, and you can see in this example, uh, uh, this is a central square array, and this round is around 100 kilometer, and we are trying to monitor all the domestic flight movement, and you can see the flights which are coming. This is a red indication. A red color is a Pune airport, blue one is a Shirdi airport, and the flights which are moving, we are monitoring them because these do transmit at their respective allocated frequency, but some of the frequency which are very near to GMRT observation band, and we want to monitor them. So this purple line you can see, this is a SpiceJet plane which is 84 kilometer away from the main electronics building, and which was there in this circle, 100-kilometer circle, for 12.8 minutes, and at present the current elevation is 7.8 kilometer, and uh, the speed is around 825 kilometer per hour. So this is one of our plan to monitor these flights. So here, in the radio telescope, we want to use all the filtering techniques. You can see the first one is a software solution, where you can monitor real-time prediction of satellite aircraft. The other solution is a hardware solution, where you use switchable filter bank in the receiver. Uh, After receiving the signal at in the main electronics building, during the signal processing and ADC and control, you can use real-time flagging techniques and remove the RFI signal in the real time, or offline. So after the observation, you can min- you can remove the RFI data from the observed data. So in the end, I will take only one example. This is a typical GPS spectrum of a GPS spectrum which are recorded by our GMRT antennas, and they are operating from 100 and 1174 megahertz to 1300 megahertz, and you can see the black line is transmission done by IRNS satellite. The blue line is Baidu China satellite, and these are the satellite are geostationary or geosynchronous satellite, and we are monitoring the satellite. Okay, this is the last slide from me. You can see how these satellites are affecting the radio telescope operation. So this is a band 3, in which the x-axis is frequency, and frequency is from 250 megahertz to 500 megahertz. The green color line is a spectrum just away from the satellite. So you can see these green lines which are coming from satellite, and when you point your telescope towards the satellite, the entire receiver system is going into saturation, and due to saturation you are seeing the cross products which are here, which are coming into the band. So from this, my colleague will take over. Santaji. Hello. Yeah.
Hi, we can hear you.
Yeah.
Yeah.
So good evening and happy new year to everybody. Yeah. So my colleague.
Hello. Yashwant, can you hear me?
Yeah, I can hear you, but I think we have lost Santaji for some reason. It's muted, it shows. Hello, Santaji, you're somehow got muted. You have to unmute. Maybe you can unmute him, Satya.
Yeah, I did that. Let me. Yeah, from here I can only ask to unmute. So
one confusion is that they're both logged in, both Pravin and Santaji separately. Whereas up to then he was sitting on the login of Pravin and trying to connect.
Yes.
Happened.
Yeah, he's from his side. He has to, or maybe he has to log out and log in again.
Doesn't seem to be able to hear us also, or what?
Let me type. Okay.
Hello.
Hello.
Yeah.
We can hear you.
Yeah. Okay.
Yeah.
Yeah. Do you see the slide now?
Yes.
Okay. Yeah. So it's upgraded GMRT is covering the frequency range from 100 to 15 megahertz and functioning since 202. It is project of Tata Institute of Fundamental Research, and its location is shown here. Next one is, it consists of 30 antennas spread over 25 kilometers in diameter. Here is a single disc picture is given. At present, GMRT is upgraded and released for astronomical community all over the world, and it offers seamless frequency coverage from 100 to 15 megahertz. And as we operated it, it has a threat of satellite transmissions, which was not the case earlier because of less bandwidth. So I'm discussing this artificial satellite interferences. So what is happening? There are thousands of artificial satellites revolving around the Earth for various reasons. So depending on the purpose, satellites are placed into certain orbits around the Earth, and certain frequency band is allocated to each satellite by ITU. Satellites have either a circular or elliptical orbits, different orbital periods, inclination angles, altitude, and lifespans. So this NORAD, North American Aerospace Defense Command, keeps track on all satellites and updates their orbital parameters. That NORAD keeps watch on all satellites throughout the world. So today there are more than 40,000 satellites plus debris orbiting around the Earth. So it's a cartoon picture, but situation is like this. So hence there is a lot of threat of RFI for radio telescopes. So if you see the some distribution of satellites. So it's Earth, and there are various satellites for various purposes. So outermost is a geostationary Earth orbit, and that middle one is this mainly navigation satellites, like Galileo, GPS, Compass, GLONASS, etc. And at the lower orbits, there are this ISS, Hubble telescope, like that. Even that Iridium is also at the lower orbit. So these are these HAYU navigation satellites from various countries. This GPS from United States, GLONASS from Russia, this BeiDou from China, this Galileo from European, and Navic from India, that is IRNSS. So these most of them do radiate in L band, and GMRT is using L band for observations, and those are the main cause of RFI. Okay, so we have identified a list of satellites. We have right now we have 148 satellites which do affect the GMRT bands. So here are a few satellites listed. It's BeiDou, Navstar, MEOS, UFO, IRNSS, which are from India. Okay, so this is just listing, and these frequency bands are also listed here. Okay, my next slide is the nature of satellite interferences. So how this satellite interferences affects GMRT observations. So what happens, this satellite RFI is not a continuous RFI. So it is like a solar eclipse kind of phenomena. Whenever a satellite comes in the line of sight between the antenna and the target source, that time this radio telescope picks up the satellite radiation. If that satellite is away, you will not get that radiation, so you will get good data. But whenever that satellite comes in between the star and antenna, you will get the RFI. So here is a cartoon picture is drawn here. At T1 time, the band was clean. This is at L band. So band was clean. So satellite was away. Whenever that satellites come between antenna and star, you will see the RFI. This T2 time, this band shape is given for a timestamp T2. So there is RFI. And after some time, timestamp T3, the band again became clean. So this is how the nature of this satellite RFI is. This first slide was geostationary satellite, while the next slide is for new non-geostationary satellite. Okay, so next one is so this is the zoomed slide for that T2 timestamp when the satellite was in between the antenna and the star. So this is how our L band is getting affected. This is 200 megahertz band, and this RFI is produced by China's navigation satellite, BeiDou G5 satellite. So it affected the almost the entire band, which is showing the saturation effect in the band. So next, so this is how the nature of satellite RFI is. So what are the solutions on it? So one can ask a question whether it is possible to find this timestamp T1, T2, T3. Means whether you can get some idea about this when that coincidence comes, that satellite thing comes, and we get corrupted data. So yes, that is possible to know this timestamp well before the observation. What can be done by knowing this timestamp? So by knowing this timestamp, one can restrict the observation, supplying the observation, observing sequence of the sources, interchange of calibrator sources and targets, shifting the observation band if possible, flagging the data for this timestamp while analyzing the data. So multiple things are possible. I mean, there are solutions on satellite RFI. So we'll proceed for it. So how do we predict the satellite RFI? So technique is simple, as we know the orbits of each satellites. If we know the orbits of each satellite, we can get its position in the sky while observing. So get the satellite orbital parameters which are free and maintained by NORAD, NASA, and satellite position can be calculated. Means AZ and EL can be calculated.
then get the satellite frequencies. We should know the frequencies of these satellite uplink and download frequencies. Then comparing the satellite position and star position, one can get this timestamp. So GMRT has maintained these satellite orbital parameters data sets for UGMRT observing bands. So from this logic, we have developed various tools at GMRT. So these tools are, we should have these orbital parameters. So a few sites have given these orbital parameters as a free, which are reliable for next 15 days or so. So first tool is automatically downloading these satellite orbital parameters called TLE, two line elements. The second tool is we'll have to track the satellite for how much that satellite affecting the GMRT. So we do call it as a characterization of satellites. So for that we use this tracking tool for satellite characterization. And next tool is predict satellite passes for upcoming observation. Then next one is real-time satellite monitoring while observing. And fifth one is offline satellite passes check. So offline passes also we can check whether it affected the GMRT observed data. So we'll move for tool one, first tool, which is a satellite download tool. So every day we used cron job to automatically download the selected satellite orbital parameters from these websites. So there are two, even more websites are there which do provide authenticate and authenticate this satellite TLE parameters. So one is cellstrike.com and other one is n2io.com. So we have kept this cron job running, and we have backup of these TLE parameters since February 2016. So next tool is track satellite for RFI characterization. So we have made a web-based tool for tracking the satellites. So we already have the satellite orbital parameters database. So from this database, we know the satellite orbital parameters, and hence we have position of satellite with any time with us. So from this timestamp, GMRT antenna do track satellites. So for characterizing the satellites, means measuring actually strength of the RFI, our RFI team tracks the satellites, collect the data, and check how much it affects the observations. So for this purpose, we use this satellite tracking tool for characterization purposes. So till now we have characterized almost 141 satellites. Okay, our next tool is predict satellite passes for upcoming observation. Uh, these orbital parameters are valid for next 15 days in future. So it is possible to predict, suppose some user has observation tomorrow or in next week or so, he can check whether his observation will affect by satellite RFI or not. So for that purpose, we have developed this tool. This tool provides proper inputs to the user so that user can take care of his targets by shuffling. If there is satellite, then he can reschedule his observation within the same time window. So this is also web-based tool that user astronomer has to input here his time, total observing time, lower elevation limit, then angular separation within the zone of avoidance, how much that satellite should be away like that, and selecting the GMRT observing band, and using his target coordinates RADEC, which are equatorial coordinates, and he can generate the passes, and before his observation he can check it, and at the web-based tool he will get the result. So first he will get the summary in text format. So suppose he has this 3C286 source as a target, then he will get this timestamp. For this timestamp, this satellite name star 61 from USA, and which will give you the list up here. Yeah, so this is the summary, and next slide is a graphical presentation of the results. So if you see this red line here, red line is the path of the source. So this is how the users, astronomers, astronomical source will move in the sky, and these thin lines are the satellite passes. So these are the three satellites. First one is Neostar from USA, second one is IRNSS from India, and this Galileo from Russia. So you see, these are the zone where it will definitely affect the observation. So these are encircled by these small circles are shown. So these are the zone of avoidance. So these zones means this timestamp should be avoided by the user so that he will get the clear data, RFI free data. So next slide is a real-time satellite monitoring. So we also developed a tool, which tool will, while observing, this tool can be used. So it will indicate the possible RFI radiating satellite while observing, which are close to the user's target. So for this purpose also we have online tool. So while observing, means while doing the observation, user can monitor this tool, and he will get the real-time display of the source and the satellites which are moving in the sky, and user will get alert, or he may request to control room to change the observing plan on real-time basis. So this is how the real-time display is shown here. So this red cross is the user's target, 37147, and these are the satellites moving in the sky, and their names are displayed here. So this is how this tool works, and it helps user. Yeah, so next slide is audio alarm in control room. So for control room, it is not possible to monitor all windows visibly at the same time, because there are various things to monitor for control room. So this audio alarm in control room helps control room operators to keep a track on these satellites which are come closer to the observing target. So if the angular distance between the satellite and user's target is less than the specific value, uh, which is plus, right now the default value is plus minus 2.5 degree, and then the system generates audio alarm in the control room as a warning message, so that either user or a control room person can take the decision where to continue observation or to change slide plan of observing. Yeah. So next tool is offline satellite passage check with recorded data file. So suppose we forget to keep track prior to observation or while observing. After observing, one can do this offline passage check. So from LTA file data, one can check whether there was any possible satellite cross during the observation. So this is offline tool that is available at GMRT site on the data analysis machine. So user can use this tool to check for fast analysis of his data, and the user can flag his data from the summary generated from this tool. So this tool generates the text summary. So like this here, scan number 5. This tool, this tool has generated this summary that the satellite BDU was closer to the source at L band for these many timestamp. Total overlap time was 3 minutes. So the user can flag that much data, and he will get the good observing data, which will result into good imaging or something like that. Yeah. So finally, the summary is this. All these tools are working satisfactorily for last 5 years or so, and many users are using these tools, and which are very helpful while observing. These are the references, and after this I'm going to give you the live demo of these tools. So we will move towards this live demo. So I'm stopping the share of the screen and share the other screen. Yeah, so this is our GMRT website where these all web-based tools are located. So these are the satellite tools. The first tool is predict satellite passes for observing. So this tool can predict the satellite passes. So this is the tool. So here user can enter his targets. So let me take one target. So this is the astronomical target 3C48. Today his time is a user has to enter the time. One can enter future timing also. Total observing time, let's say 4 hours, next 4 hours, elevation limit, and separation angle, let's say 5 degree, all band, and I can say generate the passes. So this tools looks for all listed satellite. So we have a list of 141 satellites. So this tool calculates all target passes of the satellites, compares with the astronomical source. Yeah, so it gave this summary, text summary, which shows that this meridian satellite is there from timestamp 1927 to 1948. For this time, this satellite is close to the target. Then other satellite is Navstar. The same summary is presented graphically. You see, this is the path of 3C48 astronomical source, and these are the three lines of satellites. So first one is Meridian 4, second one is Meridian 6, and last one is Navstar 69. So these are the cross sections are the timestamp where your astronomical data will get affected by these three satellites. So by using this tool, this user will get a prior information that at this time I will have to slightly change my observing plan so that this satellite RFI can be avoided. So this is how this tool works. So next tool is track satellites. So this tool is used for tracking the satellites. So one can select any one satellite from our list, and it will generate the command file, and that command file will be fed to the control and monitoring system of GMRT, and it will track the satellite. Yeah, so so I just gave the satellite, which is a international space station. So this is its path, and today it is going over the GMRT sky, and this path is traced for plotted here. So this is how we track the satellite with GMRT antennas. So yeah, so next tool is real-time satellite monitoring while observing. So right now some pulsar observation is going on, and we'll monitor it. So right now the source name is R2, which is being observed at 610 megahertz at band 4 of GMRT, upgraded GMRT. And you see there are many satellites in the sky. I just opened the filter, that's why it is showing many satellites here. but I have here zone of avoidance limit. So if I make it to some 10 degrees or something, yeah, so within 10 degrees there is only one satellite in the sky which is near to that source. So that satellite is Cosmos 2, which is near to the pulsar source. This R2 is a pulsar name that is right now being observed, and the source is 9.6 degree away from that satellite. Yeah, so this is how this tool works. So user can keep eye on this tool, and he will get the information about how close are the satellites in the sky. So next tool is offline satellite passes check. So one has to be on the real system to check this. This is not a web-based tool. Uh, Sorry. Yeah. Then the other tool is alarm tool. For getting information, we will have to be in control room. Yeah, and here is the list of satellites. Yeah, so this is that list. We have total 141 satellites here at various frequency bands of GMRT. Yeah, I think my thing is over.
Okay.
Yeah, we can proceed for question and answers. Pravin is also here.
Okay. So thanks, Hansi, and also thanks, Pravin, earlier for view of all that, I think, I mean, to some extent, RFI mitigation is a very tiresome and thankless job for astronomy experiment, and it probably requires not one but multiple strategies, as you looked at both hardware, software, and sometimes very creative strategies. And you also mentioned about the coexistence is the keyword, because you can't ask the rest of the world to kind of keep quiet because you want to observe uh, astronomy observations. So there are many things happening, and these days it's only kind of going up. And also a lot of legwork and keeping such a maintaining excellent relations and coordination with people in the vicinity, and all the way you going and trying to repair and set up their set-top boxes or DTHs, etc., is a fantastic effort. And it may not be wrong to say that the quality of astronomy data can at best be as good as, to the extent that you can mitigate RFI, ultimately the quality of the data. So congratulations to both of you and your teams for obviously doing wonderful work. So that there are some questions to today's speakers. Please, those of you who are on the Zoom can kind of ask questions directly. Meanwhile, I just have one question from the YouTube. This is from Abhinav Chaudhary. This is a question slightly more generic than today's topic, but why the meter wave length part of the radio spectrum has been particularly chosen for study with GMRT? None of you want to answer it, or you want Yashwant to pitch in, or
maybe I could just comment on that.
Yes.
So there are two kind of main reasons. One is that when the GMRT was conceived of at that time, there was a shortage of low frequency, high sensitivity radio astronomy observatories, because many of the astronomy observatories were coming up at higher frequencies for various reasons. And RFI interference is one of them, which is easier to operate at slightly higher frequencies in those times. So even those bands are now under threat due to man-made transmissions. And the second one is that there's a very powerful signal from the universe, the signal from neutral hydrogen gas, which when seen from faraway distant objects So its rest frequency is at 1420 megahertz. And when it is seen from faraway objects such as distant galaxies and so on, due to the expansion of the universe, it is redshifted to lower frequencies into the meter wavelengths. And so that was also one of the reasons why the frequency coverage of GMRT was chosen to go from 1450 megahertz and downwards to lower frequencies. So it's optimized for certain kinds of science that can be done at these frequencies.
Thanks, Ashwin.
So I have a question. May I ask
Yes.
it?
Yes, Krishna.
Yeah, and perhaps this will be best answered by Yashwant, though I don't know. See, I was intrigued by the fact that you're using ultrasonic detectors for zeroing in on elements from power lines and their structures, which generate radio frequency emission. So, where does the ultrasonic come in? Is it because of mechanical oscillations induced in the substructures that are fitted on the pylons and other such things?
So that actually, Pravin may be even better placed than me to answer. Pravin,
Okay. Yeah.
can you?
So,
Yeah, actually the ultrasonic detector which works at 40 kilohertz frequency, whenever there is a spark or gap at a pin insulator or sparking fuse link, you get all kind of radiation from extremely low frequency to very high frequency. And one part is ultrasonic wave where you can pinpoint the source of radiation.
so are you saying essentially that mechanical oscillations are induced in these objects? See, sound is involved.
Yes.
So,
Yeah, when you hear actually whenever there is an arc, you can see some audible sound. Okay. Sparking, due to sparking, you can see that sparking, we can see as well as we can hear that sparking. So that audible sound, it covers your audio range as well as ultrasonic frequency range.
thank you.
Okay. Thanks, Pravin. Are there any more questions to today's speakers? Let me also see if there are any questions from YouTube. No? Okay. If not, so once again, let us thank both the speakers today for their nice coverage of not only just the efforts, but also the nice online tools, and very, very nice the way the entire system has been up and which can aid the astronomy observers. So with that, let us thank Upgraded GMRT for conducting this talks, and we do have one more in the line of these hardware talks, namely on one of the most important aspect of these giant telescopes, namely the servo systems. So that we are going to hear next week. So with that, that's all we have for today. Thank you very much for joining. Thank you for the speaker.